it, turn it, leave it, stop, format it, touch it, bring it, fade, watch it, turn it, leave it, stop, format it, touch it, bring it, fade, watch it, turn it, leave it, stop, format it.
In section 3.5, we looked at compound interest, and we used that formula to work out a variety of problems, some in which the interest was compounded annually, sometimes semi-annually, monthly, or even daily. Well, in this section 3.6, we're going to be looking at continuous compounding, where interest is compounded on a continuous basis. There's going to be a whole new formula for that. And you'll see that there are just a few terms here. You may notice the first one is limit. Some of you may have touched upon that concept of limit in pre-calculus. If not, don't worry about it. We'll be going over what it means and exploring the whole concept as we get into the concept of continuous compounding. Make sure for the last term here, continuous compound interest formula, that you, when you look up the definition, that you not only write down the formula, but also be sure to record what each of the letters in that formula stand for.
Okay, so welcome back, guys. So in our lesson today, we're going to talk about the learning target. I can use the continuous compounding formula that allows one to compound interest every hour, every minute, and every second. So we want to talk about a more powerful way of looking at compounding interest. All right, so on your worksheet, I start out with the question, given the function h of x with where the denominator is 8x minus 3, and my numerator is 8x minus 3, my denominator is 4x plus 5. As the value of x increases towards infinity, use a table to find out what happens to the values. So guys, easy peasy. What I wanted you to think about is this idea of more or less looking at these values in a way where we could just throw them in our calculator and get back a reasonable answer. Put this on pause. Okay, I'm set now. All right, so guys, the first three choices of the table are filled out. Now, how do we get this fourth table? Well, what I'm going to ask you to do is go into your calculator, and I want you to second plus 712 second plus 712 will clear it out. And what I'm doing here is I want you to store 9,000 under x. And that's done by doing this. Hit 9,000. All right, 90,000. Oh, excuse me, 900,000, right? So we have a total of 5 zeros. Store key is right here. So that's going to be stored under x. And then what we're doing is we're putting in this equation where we have parentheses 8x minus 3, close parentheses, parentheses 4x plus 5, close parentheses. Or you could have shortcut this by just doing alpha y1. Alpha y1 would have given you the same thing. And when I hit return, I see this is my first number here. All right, so I see it's doing what? It's getting bigger. This number is bigger than the previous, this number's, and now this number's bigger than this. Well, if I do that again for 8 million, right, I will get this number. All right, and I stick it there. If I do this again for 50 million, I will get this number. So the truth of the matter is, where we're going with this is that as the value of x increases, the value of the function approaches 2. So as my x values get bigger, my Y values, they're getting bigger, but they're stopping at 2. So the limit is 2. All right. Let's consider question 2. If we deposit $10,000 at 3.85% simple interest, what would your ending balance be after 3 years? Okay, well, we're going to kind of go back to what we've done before, right? All right, this is the simple interest formula. Okay, so what are we doing? Okay, I put my principal in, put my rate in, put my time in, and what I will have an ending balance. Okay, I'll have an ending balance of my interest plus my principal. Ooh, I see what Mr. McCray was looking at that made me wonder what the devil was going on. This has to be here, and this will make the biggest difference in the world. Okay, this has to be here. Okay, that makes it much better for me. Yep, interest, and somehow I've left out 3, so 3 should be in there too. So, oh gosh. All right, I'm back. I made a quick correction. So yeah, so we should be good with this. Simple interest formula. I take my principal, my rate, and my time, multiply together. I get my new interest, add that interest back to the original balance, and boom, there we go. All right, now, move on. What would be your ending balance be if the interest were compounded daily? Ah, so if the interest was compounded daily, all right, what we would do is we would basically use our compounding interest formula, which is right here. There's our principal. We throw in our rate, the number of times it's being compounded, this is daily, and the number of years. And we'll notice that our number here of $11,224.28 ought to be bigger than our simple interest formula. And it is. Well, let's progress. Now we're going to talk about this PERT formula. The PERT formula. Well, the PERT formula is my principal, 10,000, E, which is my exponent, R, which is my rate, T, which is my year, okay, should give me more than what I had with my compounding daily formula, which is $11,224.35. Okay, so if we were just comparing apples to apples, here's what we'd be looking at. All right, I'm back. Mr. McCray caught another mistake. All right, remember, math stands for mistakes allows thinking to happen. All right, here, ending balance for simple interest, boom. Ending balance for compound interest, boom. Ending balance for compounding continuously. You notice that our numbers are getting bigger.
In this video, we will look at finding compound interest when we have continuous compounds. What continuous interest means is we have an infinite number of compounds. In other words, the interest is being constantly paid into the account. When we see the phrase continuous interest, we'll use the formula A equals P to the RT power in order to calculate the final amount. A stands for the final amount in the account, and P stands for the principal, which is the fancy bank word for the starting amount. E, this new variable, is actually a constant. Similar to recognizing pi as 3.14159, we can recognize E 0.7182828459045, and going on with no pattern or repetition. Fortunately, our calculators have an E button on them. You'll either see a button that says e to the x, or you might see a button that says ln, with a small e to the x above it. If that is the case, you'll need to hit a shift or second key in order to select e to the x. R is still equal to the rate, which must be written as a decimal. T is the time of the investment, which must be written in meters. Let's take a look at some examples where we calculate continuous interest. A